So let's do a quick recap on activating effects and directing effects. Because I know I gave you guys a lot to look at on the board yesterday, and I really want to make sure that you've got a clear idea of what does what. We're going to look at our three main types of groups: electron donating, halogens, and electron withdrawing groups. Which of these are considered activators? Oh, I need to be more specific, don't I? Towards EAS. Because today we're going to explore NAS. And the roles that these guys have flip on their heads when the role of the ring flips. Which of these are considered activators? Only electron donating groups. That includes, by the way, alkyl groups, but alkyl groups are weakly activating. Halogens and electron withdrawing groups are deactivators. They slow down the ring's reactivity. They increase the transitions, they increase the energy barrier. Which of these groups are ortho-para directors? When this group is on the benzene ring, the ring is more nucleophilic from the positions ortho and para to the group. Okay, two of them. Electron donating groups make the ring more nucleophilic at positions ortho and para, and they stabilize the intermediate when the ring is nucleophilic, ortho and para to itself. Now the alkyl groups, they may not make the ring much more nucleophilic from positions ortho and para, but they definitely stabilize the ring more because you get a more substituted carbocation intermediate. Halogens, even though they pull electron density away from the ring and make it a worse nucleophile, they stabilize the sigma intermediate when the ring attacks orthopara to itself. So halogens are truly the oddball here. They make the ring a worse nucleophile, but they stabilize the sigma complex intermediate. And our electron withdrawing groups are considered meta-directors. Before we look at NAS reactions and tie all of it back into multi-step synthesis, I want to go through a mechanism with you guys that has multiple groups on it. And I'd actually like to get the groups from you guys. So rather than me giving you something, I want us to build it from scratch so we can really see how does it work. We'll invent a molecule of our own. So I need somebody to pick a number, 2, 3, or 4. Momi, pick a number 2, 3, or 4. 2. Okay, we're gonna have a di-substituted benzene. Kieran, give me a position. Ortho, meta, para. Meta. Okay. Matt, give me EDG, halogen, or EWG. EDG. Raf, I also need. I'll come back to you. Caesar, another one. EDG, halogen, or EWG. Okay, we're gonna have an EDG group and an EWG group. Nope, sorry, and a halogen group. Caesar, I'm sorry. All right, now, who did I do? Just you 3. Jenny, give me an EDG group you'd like to have.
Like, I don't know.
Okay, think on it.
Oh my god.
Caitlin, give me a halogen you'd like to see. Bromine. While Ginny works on that, Roth, give me a reaction. We have 6. Bromination, chlorination, alkylation, acylation, sulfonation, nitration. Nitration? Do you know the reagents for it?
HNO3 and then H2SO4.
Good. Oh, no, I'm sorry, I'm going to pull it back. Bromination, chlorination, alkylation, acylation, because I'm not testing you on the nitration mechanism, just on the nitration products and reagents. So we don't need to know the mechanism for this one. So one of those 4 that we know the mechanism for. Sorry.
Acylation.
Acylation? All right.
Does an alcohol work?
Yes, and alcohol works as an EDG, and we're having them positioned meta to each other. I'm actually going to redraw this. Ralph, do you mind what my acyl group is? Shouldn't really. As long as it's an R group on the other side of the carbonyl, it's all acylation. So I'm going to put a benzene ring.
Okay.
Is that okay? This is called
phenyl.
Yeah. Phenyl is short for benzene. I didn't make the rules. I wouldn't agree with it. So first, what do we need to do? We need to be able to predict the product of this reaction, which means I need to know how those substituents are going to impact the ring's reactivity. Which of these 2 substituents will direct the ring's nucleophilicity? The alcohol alone. Why? It's an activator, and the halogen is a deactivator. The halogen's role in the ring is pulling electrons away and making it a worse nucleophile, while the oxygen is putting electrons in, making it a better nucleophile. Imagine you have 2 employees at the store, and one of them runs around cleaning things and putting things in order and getting a job done, and the other one just sits there pulling ones out of the cash register. Which one are you going to credit for the store looking nice? The one that is doing something, right? Ignore any of the deactivators. They're not having a role here. How is this activator going to direct the ring? How many positions could this ring react from as directed by this OH group? There are 3. None of them are blocked. Both of its ortho positions and its para position are available. In fact, you'll notice that relative to the bromine, that's also ortho and para. Coincidence? The bromine is an ortho-para director. It is a coincidence. It's all based on these being meta to each other. So if we had picked ortho or para relationship at the start, we would be looking at a totally different setup. Now, one of your goals is not to predict which of these placements would be the major product and which would be the minor product. In fact, all 3 of them are likely to form to different ratios, and you as a laboratory scientist would probably have to separate them using chromatography or something. Now, we could say that this ortho position, ortho to both groups, has a lot of steric strength, and it's likely to be the least reactive spot. But then it would be hard to say which of these has less steric strength. So what I want to do right now is draw all 3 possible products, but we're going to pick one of them to show a mechanism for. There's one. There's 2. There's 3. Why am I allowed to abbreviate the benzene ring as pH, but I can't abbreviate this other benzene ring as pH? It's substituted. Yeah, it matters where those groups are placed. So I can't just put pH, OH, Br. It doesn't describe to me the placement of all of those groups on the benzene ring. So because this one is mono-substituted, it's fine to abbreviate. These ones, I can't. All right, any preference for any of these products? Para to the OH? Good. I like that one too, mainly because it would be the easiest to draw. All right, we're going to draw the mechanism. What's my first step? Good. Yeah, Lewis acid-base reaction, or the acyl chloride, the acid chloride, reacts with the catalyst. What charges does this generate in my reaction? Positive on chlorine, negative on the aluminum. My catalyst is doing its job. It's starting to pull electrons away from my carbonyl. What happens in my next step?
The electrons of the ring attack the chlorine?
Not yet. No, the ring won't attack the chlorine. It would if it was chlorination and we had ClCl, AlCl3.
The chlorine has to pop off.
Chlorine cleaves and leaves me with a resonance stabilized carbonyl cation. So I'm going to draw that resonance stabilization. In addition to drawing my aromatic ring back down and my AlCl4 minus. Do I need to show electron arrows in my resonance forms? Yeah, it would be best to do that. So lone pair on oxygen is donated to form this carbon-oxygen triple bond. Do you know there is another way to show this? When we show an electron arrow pushing mechanism, it's something plausible. I could have showed oxygen sharing its lone pairs right from the start, and I would have generated this. And then I could have shown the resonance form where it puts the positive charge on carbon second. So there's different ways to do this. Does it matter which of my resonance forms I attack now? Why does it matter which one I attack, Susan?
You said not to double down.
Good. I don't want you to double up on a structure. Double up, double down. What is the difference? I don't want you to double up on showing arrows to this structure. If this structure is already being shown, forming this structure, then you can't do anything else with it. Now, does it matter which of my alkene bonds, those aren't alkenes, which of my pi bonds I use to attack my carbonyl? It does matter because I'm aiming to show the para-substituted product, well, para to the alcohol, which means that I need the carbon that is para to the alcohol to attack, and that carbon uses these electrons. So you guys agree we have to start from this pi bond? This pi bond attacks the carbonyl, breaks the triple bond back open. Br, OH, carbonyl plus H, and I've got AlCl4 minus still off there on my side. Do you guys remember I called that H something specific? I want you to draw that H out so that it reminds you you need to react with it later. But I tried to call it something specific. It's not benzylic. No. Benzylic is on a carbon off of the ring. This was the hydrogen on the nucleophilic carbon. So I'm calling that the nucleophile's hydrogen. That's the hydrogen that needs to be substituted. The carbon is currently in the process of substituting it, but there will be a step here in a minute where it gets removed. So I want you to draw that for your sake. There's a lot of different ways to show the arrow pushing here. But I'm going to try to go just about one arrow at a time. High electron density to low electron density. My carbocation is the low electron density. What do you notice about the placement of the carbocation here? Anything? It's not tertiary. It's on a carbon attached to two carbons. So it's technically still a secondary carbocation. But you're pointing out that it's connected to what?
The alcohol.
It's connected to a group that can donate its electrons. So what should my next resonance form look like? Oxygen shares its electrons. It's doing its job, and it's creating this stabilized resonance intermediate. Now for another resonance form. I'm not going to just show this double bond breaking back to the oxygen, because all that would do is recreate the resonance form I had just before it. So I'm going to do two arrows in this resonance step. This next pi bond also moves over. Gives me now a new carbocation. You know, I worry to point this out because I'm not trying to confuse you, but I love the way this resonance structure looks. Don't you? All those parallel double bonds. It scratches something in my brain, you know? It just looks so nice. But these other ones, I mean, this one's okay. These other ones are not my favorite. What do you notice now about this resonance form? It's got a carbocation next to a group that can share its electrons. We're not calling the halogens electron donating groups because we want to keep them distinct from the groups that are truly electron donating. But they do have a lone pair that they can donate, which is why they stabilize the reaction that occurs ortho or para to themselves. What does that do to the bromine?
Positive charge.
Gives it a positive charge. Is that enough resonance forms for you guys? Most of the reaction is what? Resonance forms. That's a big part of your mechanisms going into your unit test this weekend and going into the exam, the midterm exam in a few weeks. The mechanisms that you'll have to show have a lot of resonance forms. So I want you to be thoughtful about resonance. Do you still worry a little bit about predicting resonance? Then look for that trend. It's almost always this 3-atom system where the positive charge moves, except in the event that you've got a group that can share its electrons. All right, I'm gonna put AlCl3 minus down here. I'm putting it closer to where the nucleophile's hydrogen is, because chlorine will take its electrons, deprotonate the hydrogen, and the hydrogen reforms the aromatic ring. And
The double bond with your donates.
good. And the bromine takes its electrons back. How many resonance forms are in this structure? 5. How many resonance forms could be shown forming the product? 5. Any of these resonance forms could be the last resonance form. Any of these resonance forms could be drawn, being deprotonated and going into the product. It really just depends on how many arrows you want to show. For instance, I think this one maybe requires the most arrows. Deprotonate the hydrogen, reform a double bond, move this double bond, and move that double bond back out. All of the resonance forms can work. So if your electrons start in a different place, your resonance form is going to start in a different place. And then your last resonance form might look different. So I want you to be comfortable drawing the last step from whatever resonance form you have. Okay, we did it. What do you guys think? Do you have thoughts, questions, concerns?
When we're drawing, like, we're just drawing the products and stuff, do you always want us to draw all 3 products? This would make it like we're not doing a mechanism and we're just drawing products.
Hang on, one more time for me.
So if we're just given this reaction and we need to draw the products, do you want us to draw all 3 of them on like all the positions?
Yeah, you know what? I try to be as clear as possible. So there is something to be said about this position that's not preferred can also form a product. It would be the most minor product. My goal is to make it clear how many products I want to see.
Okay.
Or it's flipped, and it's which of these are possible products from the reaction. So if I had showed all 3 of these, and then a 4th one, and I said which of these is not a plausible product from this reaction, you would have picked the 4th one.
Okay. So yes, draw them if depending on how you ask the question.
Yeah, the question will probably make it clear
Okay.
what's needed.
Okay.
Now, if you're doing a multi-step synthesis, like if this was just one part in your process,
Uh-huh.
how would you know what to do? What if I could form this and this and this, but I only needed this one for my multi-step synthesis?
Uh-huh.
I encourage you guys to just show that one. If multiple products can form that include the one you want, just show the one you want. The idea is that if you got into the lab and had to synthesize this, you would have the skills to separate it.
Are you gonna want us to show all the resonance groups as well?
Actually, here's a challenging thing. I try to be very intentional about how I grade mechanisms. Not just mechanisms, I try to be intentional about how I grade problems. So I assign points to a problem based on, especially a mechanism, based on what it's worth and what I'm expecting you to show. So a mechanism like this would be 1, 2, 3, 4, 5, well, probably 3, 4, 5, 6, 7, 8, 9 points. It's a 9-point mechanism. I could scale it and say 18 points, and then I've got 2 points per step, including mechanisms. That way that if you forget your charges or your charges are off, I've got points per step that I'm looking for your charges. If you've got arrows that are missing, if you use a reaction arrow instead of a resonance arrow, those are all things that I look for in the mechanism, and so I try to assign 1 point per step. The challenge there is not every step has the same number of arrows or the same number of charges. So I could also assign points by the individual components. I need to see a lone pair, I need to see an arrow, I need to see a reaction arrow, 3 points. I need to see 2 charges, maybe 1 point, and an electron arrow. Then I need, so there's a lot of different ways to do it. What I try to give you guys is a checklist. Make sure that you show me all resonance forms, show me all relevant lone pairs, show me all charges, and all byproducts at each step. I try to give you that checklist so that you don't have to guess. Oh, is he looking for all the resonance forms or is he not? Is he expecting me to show this lone pair or is he not? But then you don't have to worry. Honestly, you can actually try to use it to your benefit. You look at a mechanism and it's worth 6 points. Guess how many steps it probably is? 6 steps. Or it's 4 steps and it includes 2 resonance forms. So you can try to use the points to actually help you understand the mechanism more. I don't like giving a mechanism and saying 10 points. I'll figure out how to take points away from you. So here's the challenge with that. When I give you mechanisms on an exam, I always give you at least 2 choices worth the same number of points, which means they have the same number of steps, the same number of components. Or I try to do that as best as possible anyways. In the homework, I guess I didn't check if the homeworks have the same number of steps actually.
What is
2 different choices, probably is the same number of steps. I just need to check again. But on the exams, I'll do that. Same number of steps, even if they are drastically different reactions. All right. Do you guys have questions on this? Oh, I've got one question. Which of these resonance forms would be considered the major resonance contributor? Sorry? Sorry, which of these resonance forms? You're like Vanna White. Which of these is the major resonance contributor? Let me number them so we can describe them better.
Can you remind me what makes it? Oh yeah,
Yeah, a major resonance contributor is one that is more stable. What makes a resonance form more stable? Let's go through the list. What's the number one priority?
Charges.
Minimum charges. But that's almost never the case. What next?
Octet.
Maximum octets. And lastly, charge placement. A positive on a less electronegative atom, a negative on a more electronegative atom. What do you think?
Make 5.
Do you guys agree with Caitlin that 5 is our major resonance contributor? What would you debate? 5 or 3? So what do they have in common? They have maximum octets, no carbocations. Do you guys remember when we first did our mechanisms, there were 3 resonance forms? Carbocation, carbocation, carbocation. So for each group that can share electrons that is placed correctly, you increase a resonance form.
I think number 3.
So what's your rationale behind 3?
Because the pi bond of the oxygen also is conjugated with the other pi bonds of the ring.
And is that not true for the pi bond to bromine?
No, it only has 1, and the other one has 2.
I see a double bond to bromine and a double bond to oxygen.
But it can go both ways.
Oh, okay, so you're saying that the oxygen could share its electrons in either direction, but the bromine can't share its electrons here? You've got an interesting idea, but the way I would frame it to you is that there is a non-aromatic conjugated system that runs from bromine to carbon to carbon to carbon to oxygen to carbon to carbon. Kind of a whole conjugated system. So I would say oxygen and bromine are equally conjugated, but you've got a good idea. I want us to come back to Caitlin's perspective, which actually followed our 3 rules. Same amount of charges, but maximum octets, and bromine is less electronegative than oxygen. You know, the thing is, I would almost never have you compare bromine to oxygen. So this was kind of a unique case. We built this reaction ourselves. Would you guys agree? Actually, what I often have you compare is when oxygen has a positive charge versus nitrogen. Because nitrogen being less electronegative, but also equally polarizable, it's a lot harder to, or it's a lot easier to feel confident. Nitrogen takes a positive charge better than oxygen. One of the reasons nitrogen is a better activator than oxygen. There is something odd about bromine, which is it's less electronegative, but it's very large and polarizable. So I don't know how well it shares its electrons and how well it actually holds that positive. So in your exams and your tests, if you see a comparison between 2 structures like this, it's almost always going to be O and N, and priority goes to N. I would say in this example, I'm not confident, and we're going to say it's either one of these is probably the major contributor. And honestly, probably oxygen, given the fact that it is actually the activator for the ring. I think that it does a better job sharing its electrons, even though it is less electronegative. So in that 3rd rule, appropriate charge placement, this is a challenging one, and it's not one that I would put on your test. So maybe now I will. No, I'm kidding. Maybe a bonus problem. I'll give you this and say, regurgitate why I said. All right. Questions before we leave EAS? You guys are sad to leave EAS already. All right, we're going to talk about NAS reactions, also called SNAR. How does the ring behave in an NAS reaction? Substitute the aromatic ring with a nucleophile. So the ring is an electrophile. Is that different from what we had here? Yeah, we're going to see the ring be attacked rather than the ring doing the attacking. You'll recognize SNAR is similar to SN1 and SN2, but it's not an SN1 mechanism, it's not an SN2 mechanism. It is the nucleophilic substitution on an aromatic ring mechanism. There is an important thing about aromatic rings in NAS. It requires an aryl halide. So a nucleophile, this is a generic version. A nucleophile will donate its electrons to the aryl halide position, and that will break one of the aromatic pi bonds into the ring. Nucleophile bonds to that carbon, which pushes. Wait, we had all these positive charges before on my sigma complex. What do I have now? Negative charge. So the sigma complex intermediate is an anion now. What group could I put on a ring that would help stabilize a negative charge? An electron withdrawing group. A group that pulls electron density away from the ring, stabilizes that intermediate. So electron withdrawing groups are now activators. I'm not going to say now, that's just, they are activators to NAS, and they are orthopara directors. I'm going to be a little bit more specific, and I'm going to say they're orthopara aryl halide directors, because NAS requires a halogen being a good leaving group. Electron withdrawing groups are the activators to NAS. They lower the energy barrier. They make it easier for the reaction to occur. They stabilize the sigma complex intermediate. And they do that when the ring is substituting an aryl halide that is ortho or para to itself. Oxygen is able to stabilize the sigma complex when the ring reacts as a nucleophile, ortho or para to itself. An electron withdrawing group stabilizes the negative charge in NAS if it's substituting the ring ortho or para to itself. There is one last thing to say here, which is Electron donating groups, except for alkyls, inhibit NAS. Now I'm putting a lot of exclamation points here because I want to make sure that you understand what I mean by inhibit. We said that electron withdrawing groups are deactivators to EAS. We should expect the opposite is true. Now, electron donating groups we would think are deactivators to NAS, but they're not deactivators, they are inhibitors. If there is an electron donating group, the ring will not be an electrophile. Unless it's an alkyl. These we call weakly deactivating, or not weakly. These are deactivators. They allow it to occur still, but they slow down the reaction. They increase the transition barrier. Deactivator to NAS. So let's look at these 4 molecules. And let's ask, or let's rank their reactivity towards NAS. What are the things I should be looking for? I want to look for EWGs and EDGs, electron withdrawing groups, increase reactivity, especially when they are orthopara to the aryl halide. Alkyl groups deactivate the ring towards NAS, and electron donating groups inhibit NAS. So we would say if there's any electron donating group, it is by far the least reactive. So can you give me the least reactive on this spectrum? Can you name it? Yeah, you just need to describe the placement between chlorine and the alcohol. Metachlorophenol. Yep. Metachlorophenol. You could also call it metachlorohydroxybenzene. Least reactive. So I'm going to put this as number 4. Why? Has an electron donating group. It's not even going to go through any sort of NAS reaction. What is the most reactive in this series? Is it easy to see? What do you think, Caesar?
The first one with the ortho nitro to the chlorine.
orthochloronitrobenzene? Why is orthochloronitro better than metachloronitro? Those electron withdrawing groups are ortho-para directors. They're going to stabilize the intermediate and make it easier to form when they are ortho-para to the leaving group, the halogen. So ortho is more reactive than metachloronitrobenzene. But even metachloronitrobenzene still has an electron withdrawing group. What does this species have? It's got an electron donating group. Specifically, it's our alkyl group. So it's going to inhibit, or it's going to deactivate the ring. But at least the nitro group activates it. It's not activating in necessarily the best position, but it's activating the ring. A little bit of context. The ring needs to have electron density pulled away from it in order to be a good electrophile and accept electrons. Nitro is pulling electron density away from the ring. It's doing it better when it's ortho to the leaving group, but it's still pulling electron density away. Methyl, on the other hand, is pushing electron density into the ring, making it harder for the ring to accept new electrons. So even though these are not, even though this is not placed best, it's still having a positive effect on the ring's electron density relative to this. All right, now we could do something similar to what we saw last time as well, which is what happens if I have multiple groups or a changing number of electron donating and electron withdrawing effects. Which of these is more reactive to NAS?
The one to the right?
Why?
The other one wouldn't even react.
No, it would react on the left.
But you said the methyl was.
It's a deactivator. But things like OH, OR, NH2, those are inhibitors. Alkyl groups are deactivators.
Oh, okay. I kind of mixed it.
Alkyl groups deactivate, but other donators inhibit. Kieran, do you agree that this one would be more reactive? What's the difference between these two? Has no deactivators. It only has two activators. Good. Okay, there is another thing I want to talk about with our NAS reactions. That comes down to the actual halogen. There's this really interesting idea. When our halogen is fluorine, it places the largest partial positive on the carbon but it has the strongest bond to carbon. And then we have chlorine, bromine, and iodine. Iodine puts the smallest partial positive on carbon, and it has the weakest bond.
And then order.
That's the order of the family. fluorochlorobromoiodo. Now, given the fact that our reaction proceeds through addition followed by elimination, the halogen leaves. Which of these halogens do you think reacts the quickest to NAS?
The yodo.
The iodine? So when this is fluorine, the carbon has the strongest partial positive for the nucleophile to attack. So in theory, addition works quickest. But when this is fluorine, kicking it off means breaking the strongest bond. When this is iodine, there's the smallest partial positive for the addition to occur, but then reforming the aromatic ring through elimination, it's the weakest bond. So Raf, your idea was iodine has the weakest bond, so it should be the easiest to kick off. I'll ask you to think about it this way. Don't think about it from the alkene's perspective. Sorry, the halogen's perspective. Think about it from the aromatic ring's perspective. Which of these two steps is harder for the aromatic ring? Addition or elimination? Why? It has a charge, and it's a good start. It has to take on a charge, so it's hard for it to break that bond and take on a charge. You're not wrong. There's something else that happens when it breaks that bond, when it takes on that charge. It does. It loses its aromaticity. Here, the aromatic ring has to stop being aromatic. In the next step, it becomes aromatic again. And what's so special about aromaticity? It's this energetic stabilization. So you want to break the aromatic ring, you're going to break that energetic stabilization. You're going to reform that ring, you're going to reform energetic stabilization. So the hardest step here, we call it the rate determining step, the highest energy barrier, is breaking the aromatic ring. Does it matter how strong the bond is to carbon when you break the aromatic ring? Doesn't matter. Because the hardest step is breaking aromaticity, but that doesn't even include breaking the halogen bond. So it's not about how strong the bond is. That's an interesting thing, but it's actually about how electrophilic that carbon is. So let's look at this example then. What would this be? 1 chloro, 5 fluoro, 3 iodo, 2 nitrobenzene. Good. Would you agree that the halogens are all placed ortho or para to the activator, the electron withdrawing group? I'm going to give it, I feel like I skip out on some electron withdrawing groups. I feel bad for cyanide, so I'm just going to make it a cyano group. It doesn't matter, does it? It's all electron withdrawing. The cyano is still an activator to this reaction. Which of those halogens is going to leave first? Which of them reacts the easiest? Fluorine. Mm-hmm. And if I swap out this fluorine with a bromine, because I'll be quite honest, we're not going to see fluorine or iodine on our aromatic rings very often. It's not impossible. There's some very important compounds, especially in the thyroid, that have iodine bonded to aromatic rings. But in organic chemistry, it's a challenge to make that happen. You guys have seen we're only doing bromination and chlorination. What happens now? Which of these leaves first? Chloro. So you look for the strongest partial positive. You look for the most electronegative. And you find the most reactive halogen towards NAS. All right. Giving you a lot to think about. When we went through EAS reactions, I gave you bromination, chlorination, alkylation, acylation, sulfonation, nitration. I can't do the same here. They're not so well named. We could try to name them, like we could call it amination, hydroxylation, alkoxylation, but they just aren't named that way. Instead, all nucleophilic substitution reactions are just classified as SNAR. So let me give you some common nucleophiles. Hydroxide. Alkoxide, like methoxide or isopropoxide, etc. Ralph, does that mean that I can put water as my nucleophile?
If you protonate it before.
If I deprotonate it before. Water is not hydroxide. Hydroxide is a good nucleophile. Water is not a good nucleophile. Can I put methanol as my nucleophile, Momi? Can I put CH3OH over the reaction arrow and say, I'll do a nucleophilic reaction? It's got to be the deprotonated form. It has to be methoxide. I do want to say some students get confused because I'll put the reagents up here like this, but then you see them on the reaction arrow like this. Those are the same thing. They do look different, but you're seeing sodium, which is a positive ion, which implies that you're dealing with hydroxide. You see sodium, a positive ion, which implies you're dealing with methoxide in this case. This is this. These are the same. The only difference is that I ignore this spectator ion, an ion that's not doing the chemistry. We have some similar structures with nitrogen. Nitrogen, of course, can change between having two H's, one H, one R, and two R's. Which means here we could be looking at a structure like this. 1-propanamide. So there's this weird thing about naming negatively charged nitrogens as ions. They're called amides. IDE, indicating the negative charge. What else is called an amide? Yeah, the carbonyl family group, the carbonyl with the nitrogen. So it's really confusing. These are called amides. Functional groups are called amides too. Now the only other nucleophile that we're really going to see would be carbon nucleophiles. So that's like an R group with a negative charge. Maybe that's something like this. We'll also see it on occasion written with counter ions, and we're actually going to look at these more in the next chapter. And the other carbon anions that we might see would include acetylide ions, alkyne anions, and cyanide.
But the ones with the R minus, those two don't have any charges. Is it like the sodium?
Yeah, you see, if you see lithium, you know lithium's a positive charge, then what's bonded to it must be a negative charge. If you see magnesium, you actually know magnesium is 2+, which is balanced by a minus on the carbon and a minus on the bromine. We're going to look more at those reagents at the start of next week. So do you guys remember last week I said, earlier in the week, we had that list of electron withdrawing groups and electron donating groups, and then we listed out the EAS reactions, and I went through, and we put a check mark next to each electron withdrawing group that we could put on, which was most electron withdrawing groups. And we had none of the electron donating groups that we could put on, except for alkyls. Now, I can put on my electron donating groups. Now I can get nitrogen groups, I can get oxygen groups, and I can even add carbon groups in a unique way as well. Most of the time, you're going to see a reagent like this. So let's look at some reactions, and what we'll try to do is predict a product, predict a reagent, and predict a starting material. So we're going to do 3 practice problems here. putting that up to remind myself. Don't be sorry. That's right. And going back to reviewing your notes, that's the only way you'll remember which ones are which. Do these reagents remind you of the reagents we put over the arrow for EAS reactions? Like when we did EAS reactions, we had Br2 FeBr3, Cl2 AlCl3, alkyl halide AlCl3. They don't look similar, do they? There's no catalyst that's making these reactions run more easily. And the reagents are all nucleophilic. They look very different from the reactions from EAS. So you can usually tell those two types of reactions apart just by the reagents that are written with it. Do you guys making some progress?
Mm-hmm.
Are you feeling stumped? You what? Oh. Mm-hmm. Yeah. Yes. So this one, how many right answers were there? Yeah, it could be this, CL, BR, or I. Maybe. This is actually para to this position, which means this group is activated the most. So it wouldn't matter which one. But you are right that by picking the difference that you did, you really prioritized that position. Yes, these two are right. Yeah, you got it. You're saying no change? Oh, okay, just starting. Yeah. This looks like a good start, by the way. What you erased. Mm-hmm. You're not wrong.
Like what leads? What's a good lead?
Yes, what is a good leading group? Actually, before I erase this, I had a rule up here. I think it was maybe the second thing. Requires. All right, I want to go ahead and start putting some of them up on the board for us. What's my nucleophile in this reaction? Hydroxide. So I'm just going to substitute Br and OH. I'm going to do it in a different color. So I went from having bromobenzene, and I now have phenol. I've substituted the bromine. EAS substitutes a hydrogen. H gets removed, a new group gets put on. NAS substitutes an aryl halide. Are there any activators in this reaction? No, just the leaving group. This reaction does have an activator. It's got the carbonyl. I'm not substituting the carbonyl. The carbonyl is going to help me substitute the chlorine. and I need the chlorine to be substituted by an NH2 group. Can I put this? That's a neutral molecule, that's ammonia. But look what it isn't. It isn't negatively charged. It isn't a strong nucleophile. So I would need to work with NH2 minus. There's another way that I could write this as well. I could say something like sodium amide. Those are identical to each other. All they do is specify a counter ion. How did I predict that so fast? Boop, just cut off that bond. Give the electrons back to the group. You know what your group is now. We would do the same thing if we were working backwards from phenol. Break that bond, give the electrons back to the group. You've got your nucleophile. Here my nucleophile is cyanide, and I can see that my cyanide ends up para to the sulfonyl group. The sulfonyl group is an electron withdrawing group. So sulfonyl is activating this group para to itself, which is why the iodine doesn't get replaced. Something that I know right away in my starting material, I have SO3H and iodine meta to each other. And I know that I have a leaving group at this position para to sulfonyl. If I put X as in halogen, I might, if you put X, I might take some points off. Give me something. Tell me that you know the halogens. Doesn't matter which halogen I put. Not really. Any other halogen is going to be more reactive than iodine because they'll all put a stronger partial positive on the ring. But even if I put iodine, this reaction occurs and not this substitution. Why?
Yeah.
My director tells me so, right? Sulfonyl is directing the reaction para to itself. Sulfonyl will not direct the reaction meta. So you had as many options as you would like. You could put fluoro, chloro, bromo, iodo. But even if you had them be the same halogen, one of them reacts selectively because of its relationship to the director. All right. Any questions? I want to show you guys some mechanisms. These mechanisms don't need to take very long. And what I'd like to do is actually show you guys the mechanism for this reaction because it's going to be very similar to most other mechanisms. Oops. Do you know what? I'm so used to drawing my little circle, and today that would have bitten me in the butt. I can't have that circle in there in this reaction. True or false? This reaction has a catalyst. A reagent that remains unchanged but helps the reaction proceed. What's your gut telling you? No catalyst. It's just the aromatic ring and a nucleophile. No catalyst involved. Look back at all of our EAS reactions. How many of them don't have a catalyst? FeBr3, catalyst. AlCl3, catalyst. H2SO4, catalyst. They all have a catalyst, and all of their mechanisms start with the catalyst. No catalyst, The mechanism doesn't start there. Instead, the mechanism starts by directly attacking the aromatic ring. Finally, we get to just start with the actual reaction. Now, you guys don't think I'm going to make you draw all the resonance forms for this, do you?
Yes.
Yeah, don't be silly. What byproducts form at this step?
Chlorine.
No, I see the chlorine. It's still on there. None. Nothing forms. That's it. That's my intermediate. And now I'm going to look at the resonance. What is the placement between the electron withdrawing group and the electrophilic carbon? The carbon that has been attacked. The carbonyl is what to the electrophilic carbon? What relationship? What was their ortho? And we know that these electron withdrawing groups are activators and orthopara directors, which goes hand in hand. When the ring gets attacked ortho, then the negative charge can be pulled into the carbonyl by resonance. You see how I did that? The carbon on the ring held the negative charge, held a lone pair. It shared that lone pair with the carbonyl carbon, and the carbonyl carbon gave the pi bond back to oxygen. Now I have 3 more resonance forms. Oxygen shares its lone pair back. The pi bond re-enters the ring, and the next pi bond breaks into a lone pair. Are you guys starting to see what the process is going to look like? Do you see how the reaction is on its way out? Electrons flow from high electron density to low electron density. They flow from the negative charge into a pi bond, and from a pi bond onto a negative charge. Lone pair in, lone pair out. Negative charge, lone pair, does elimination. Reforms the pi bond, reforms the aromatic ring, kicks out the leaving group. In this case, my leaving group is my halogen. So now I have a byproduct of chloride. Easier or harder than the EAS mechanism? In my opinion, it's easier because there's less to deal with the catalyst. You're dealing more with just the nucleophile. And maybe there's a little bit more to do with the arrows. In EAS, most of our resonance forms had one arrow, pi bond to positive charge, pi bond to positive charge. EAS has twice as many arrows, lone pair in, lone pair out, lone pair in and over, lone pair out, lone pair in, lone pair out. But also, I think the elimination is easier. Lone pair in, leaving group leaves. So I actually think NAS is an easier mechanism than EAS. And on your unit test, you may get an NAS mechanism, you may get an EAS mechanism. But on the midterm exam, you will have your choice between an EAS mechanism and an NAS mechanism, if I'm being generous. Otherwise, I might put 2 EAS mechanisms. Usually, though, I put one of each. So find which one works better for you. All right, I have a question before we move on, because we could do tons of mechanisms, but they're all nearly identical, where they all involve pulling electrons out. Which of these resonance forms is the major contributor? Is it 1, 2, 3, or 4? Why is it 2? Every form has full octets. So every form has the same charge. Every form has full octets. All of those carbons, they have octets. What's special about 3 or 2?
The negative
Oxygen.
charge is on oxygen.
Appropriate charge placement. Putting the negative charge on the oxygen. That's what makes this one so stable. That is the activating effect of these carbonyl groups, of the nitro group, of the sulfonyl group. They all take the negative charge and put it on the oxygen. The cyanide group takes the negative charge and puts it on the nitrogen. But it's very similar. Imagine we did a reaction like this. If we showed the mechanism for this first reaction, how many resonance forms do you predict? The sigma complex would have 3 resonance forms. Think back to when we did EAS reactions. Benzene alone to bromobenzene. How many resonance forms in the sigma complex? 3. So EAS, NAS, standard, they have 3 resonance forms. But if you get a group like electron donating in EAS and electron withdrawing in NAS, that is orthopara to your position, now you can increase your number of resonance forms, stabilizes that intermediate, allows the reaction to proceed faster, more reactive. Activators. Being an orthopara director and being an activator go hand in hand, except for halogens, which are deactivators and orthoparas. All right, questions on the mechanism? Could you guys see yourself doing it with 2 electron withdrawing group substituents? You just add another resonance form. That's all. Now let's put this into the context of multi-step synthesis. I want to go from bromobenzene to 1-bromo 5-nitro toluene, or 1-bromo 2-methyl 3-nitro benzene. Brainstorming tells you that I need to add a CH3 group, alkylation, and I need to add a nitro group, nitration. And I can try to work forward and backwards to figure out which of those two reactions needs to go first. Bromine is what type of substituent? It's a halogen. But on the ring, how does it change the chemistry of the ring? It's a leaving group in NAS reactions. But these are both EAS reactions. It's a deactivator in EAS. And what kind of director? Orthopara director. So can I take bromine and run nitration and put the nitro group where I want it? If I take bromobenzene and run nitration, how will the nitro group be placed? Ortho or para. But I need it to be placed meta. So here's some analysis that I can do. This is an orthopara director. This is an orthopara director. This is a meta director. This will never be the director because it is the most deactivating group. And this will only be the director if this is not present, because methyl is a stronger activator, a weak activator. Halogen is a weak deactivator. So if I'm starting here, I can't create a group that is meta. My only option is to start with bromine and add an ortho-methyl group. Now, one of my suggestions to you guys earlier was if a reaction gives you 2 or more products in a multi-step synthesis, but you only need one, just show the one. What reagents would I need there? It's going to have to involve methyl.
CO, methyl, and then aluminum chloride.
Good. Chloromethane and AlCl3. Now I have 2 orthopara directors, but which one is going to have the role of director? The CH3. It's a stronger activator. So now I can run nitration, HNO3, H2SO4. Okay, so I'm running out of time to help you guys do some practice, but I want to leave you with this, this rather interesting one. From benzene to metapropylphenol. How do you get an alcohol onto an aromatic ring? EAS or NAS? NAS. The alcohol can only be added if it does nucleophilic substitution of a halogen. So I know that I'm going to need to have NAS with hydroxide. And in order to have NAS, I need to have a halogen leaving group. So I'll also have to do halogenation prior to that. What other type of reaction might you expect here? Alkylation. Except I showed you guys the very first day we looked at alkylation that you can't add a straight carbon chain like that. It's going to form a carbocation intermediate, and the carbocation intermediate rearranges. So it's a trick. There's no alkylation here. There can't be. But there's another reason that we know that. What's the position between these two groups? They're meta-positioned. Which of them is a meta-director? Neither of them. They're both ortho-para-directors. So what about the halogen then?
What if it's an NAS and there's the kill group right there? In NAS, couldn't that be a deactivator, which would be also meta for NAS?
Yes, but how do I get those two groups onto the ring? So NAS just substitutes a halogen for another group, but it doesn't actually get the halogen and the other group on there.
But if I did the other group in first, then could it be a deactivator and go meta direction? No.
So if I put halogen,
No, I still have the
halogen is ortho-para-directing. If I put the alcohol, alcohol is ortho-para-directing. If I have an alkyl, alkyl is ortho-para-directing. So there's a hidden secret here, which is the Wolff-Kishner reduction. What if this wasn't a straight alkyl chain? But what if it was priorly a carbonyl, and I took that carbonyl down to an alkyl group? I do hydrazine and potassium hydroxide. So here's my route. I'm going to add this 3-carbon chain as an acyl group. Why do I put this on first? Because this is a meta-director. So now I can make sure that my second substituent ends up meta. My second substituent is iron 3 bromide. And Br2. The acyl group directs the halogen meta to itself. Now, I really have two options. I can do my, I don't know why I did it like that. I can do my NAS, my aromatic substitution, because I have an electron withdrawing group and I have a good leaving group. Now I substitute my halogen for my alcohol. And to get to my final product, I reduce the carbonyl, H2NH2 KOH.
Could you use zinc and
Zinc mercury with hydrochloric acid would also work there for reduction. It's a lot to think about. I don't think that your synthesis problems on the unit test will feel that challenging. But I do want you to have this perspective. Draw in OChem1 reactions if they're relevant. Draw in benzylic reactions if they're relevant. Multistep synthesis at this point now gets to include all sorts of reactions that we've learned about. So see how much you can brainstorm when you're looking at a multi-step synthesis. Potassium hydroxide, KOH. It needs basic conditions to, it's a catalyst, catalytic basic conditions. All right, I apologize for taking you guys over. I'll see most of you in lab today, and the rest of you, good luck on your unit test this weekend. I'll see you guys next week.